All right, so this is the Chemistry X exam review semester 2. Today we're going to discuss rates and kinetics and general equilibrium. So, question 1 says list the recognized factors that affect reaction rates. Big one is concentration of reactants. Concentration of reactants. Oh, this pen is garbage. Much better. That's a big one. Notice it's the concentration of the reactants. Remember we said that concentration of products don't really matter. It doesn't matter, for example, as prom approaches, how many people already have dates to prom. That's the products. It matters how many people don't, because that's the reactants that can collide and have a successful reaction. Temperature is a huge factor. An enzyme, or in chemistry what we call a catalyst. Surface area for solid reactants. So real quick, how does concentration of reactants change it? Concentration of reactants makes the higher the concentration, the more collisions. Surface area of a solid reactant, again, the more surface area, the higher the amount of collisions that can occur. That's why like powders and stuff like that's much better than chunks. A catalyst, it lowers the activation energy. The activation energy is the minimum amount of energy required to for a successful reaction to occur. Catalysts lower that. A temperature works two ways. It makes, as you increase temperature, the particles, the reactants have more kinetic energy, so they're going to be moving faster, which means they're going to collide more often. And they're also moving faster, which means that they have more energy for when the collision does occur. Those are big factors for changing the reaction rate. It's about every 10 degrees, the reaction rate doubles. Every 10 degrees Kelvin increase, the reaction rate doubles. So if you decrease the temperature by 10 degrees, then it would half the reaction. What effect is increasing the temperature? It increases it because more collisions and more energy. What happens to the reaction rate over time? It goes down. It decreases because you're using up all of your reactants. As time goes on, more reactants are becoming products, and thus your concentration of reactants is lessening or becoming lower, so it decreases the rate of reaction. So when is the reaction the fastest? At the start. Use collision theory to explain why reactions speed up or slow down due to changes imposed on the reaction. Basically, collision theory states they must collide. Reactants must collide with the activation energy, or the energy of activation. So any change you do to the collisions, or any change you do to the energy or the activation energy, for example, using a catalyst lowers that, that's going to impose a change on the reaction rate itself. And I kind of already explained that in here. But those are the two things. They must collide with enough energy. And proper orientation is something we always say too. Which the catalyst itself can help with that orientation. The rate law for a reaction is this. What would happen to the rate if a different trial were performed where we start with twice the molarity of O2 but the same amount of H2? So if we start with twice the molarity of O2, then that's going to be, instead of x, we would say 2x. Or if this were 2 and we doubled it to 4, then it would be 4 squared. So the best way to do it is to just say, okay, 2x would be 4, because 2 squared, it would be inside of the brackets. The 2 would be inside the brackets, and we're squaring everything in there. So twice the molarity would be 2 squared faster, or 4 times faster. Twice similarity of H2S, but the same amount of O2. So if this is X and this is Y, and now we have 2Y, then when we multiply this 2, it's going to be 2 times faster. Twice similarity and twice similarity. So this is 2 square, which is 4 times faster, times 2, which would be 8 times faster. And all I'm doing is plugging in a number in front of either the X or Y in that rate law equation. Half the molarity and half the molarity. Well, that would be 1/4. 1/4 times 1/2 would be 1/8 times as fast. Down here, number 6, for this reaction, very simple reaction, we have 3 trials, and we want to figure out what the order of each of these are. To do that, you need to compare this. This is doubling that, and I'm going to need a calculator for this. 2.4 times 10 to the negative 5th divided by, since I took 0.025 and divided by that, I'm going to do the same thing. This divided by that. 3 times 10 to the negative 6th, and I get 8. So doubling this made this 8 times faster. So we take a little formula here. 2 to the x equals 8. The order is 3, because 2 times 2 times 2 is equal to 8. So x equals 3. Remember, we could talk the log of 8 divided by the log of 2, and that would give us that 3 as well. What is the order of y? So here we chose 2 and 3 because we need no change in the 1, and we can see how this change affects the rate. Here, there's no change in x, so we can see how doubling this changes the rate. And doubling this looks like it doubles this. So the rate, or the order of y would be 1, because 2 to the x equals 2. 2 to the first power equals 2. What is the overall? Well, we just add these up, and we get 4. What that means is if we double each of these, anything we do to each of these, we double them or whatever, 2 to the 4th power would be how much faster the reaction is actually happening. It says calculate the rate law. Constant, K. So we know the rate equals K times x to the 3rd and y to the 1st. So I'm just going to pick one of these. I'm going to go ahead and pick trial 1. So the rate is 1.5 times 10 to the negative 6th, and we're going to divide that by 0.0125 to the 3rd and 0.0250. And that's going to be equal to k. Basically, I rearrange this formula by dividing both sides by this, leaving k all by itself. So I got 1.5 times 10 to the negative 6 divided by 0.0125 cubed, divided again by 0.0250 to the 1st, which is the same thing. So it looks like our k is 30.72. And the units for that, since this is m cubed, molarity cubed times molarity, that would be molarity to the 4th. So we would need to get rid of all but one of those, so it would be molarity to the negative 3rd, and again per second. That's how we get the rate. The rate is molarity per second. So when we multiply these two, we have molarity cubed times molarity, which is molarity to the 4th. We need to get rid of 3 of those. What is a catalyst? What does it have? What effect does it have on the rate reaction? How do catalysts work? So a catalyst is a chemical compound that is present during a chemical reaction, but is not used up. Not used up. What that means is a small amount of catalyst can be used, and it would be used over and over and over again. it lowers the energy of activation, or the activation energy. So if we take a normal thing where we have energy and progress, we might see a normal reactions like this. A catalyst will lower that energy needed, that activation energy needed. How does it work? It works by creating an alternate path. Alternate reaction pathway. That requires less energy. So that pathway could be like, for example, the catalyst being there, and it creates temporary bonding points for the two chemicals, and then those two chemicals can bond, and then they leave the catalyst. That's a common way for it to happen. 8. What is energy of activation? That is the minimum energy required for a successful collision to occur. The minimum energy requirement for a successful collision. In an exothermic reaction, which has more energy, the reactants or the products? The reactants has more energy. Reactants have the energy, and then with exo, the products will form and heat will be given off. So more energy here, because this is separate from the energy. Easy enough. Which of the following is the possible rate law? Well, remember, we don't care about the amounts of products for this. So anything with Y and Z is going to be taken out. And there we go. So it's going to be A, because all we care about is the concentration of the reactants. The products, the concentration of the products don't affect the rate. The following data is obtained. Concentrations are in molecules per centimeter cubed. Weird. And the rates are in molecules per centimeter cubed per second. Which of the following is the correct rate law? So we need to find something where it changes in one but not the other. So here we doubled, and here we quadrupled. So 2 to the x equals 4. That's going to be, NO is going to be of the 2 square equals 4. That's going to be second order. Then we need to find where it doesn't change for these, but it does for the other one. So I like this. You could have picked more than this, but this seems easy because it doubles, and then this also doubles. So that's going to put O2 in the first order. So we're looking at C for that. NO to the second order, O2 to the first order. Overall order would be 3. So that means if we doubled anything, it would be 8 times. If we doubled both things, it would be 8 times faster, since the overall order is third order. Tabulated below is the rate, blah, blah, blah. They want us to find the value of K. So the first thing we got to do for this is we have to look at the two reactants, right? We don't care about the products. Again, we don't care about them. We're going to look at the reactants. This is doubled in I, and this is doubled. So for I, it is first order. Here, we have this doubling, and 2, this is 4 times. So this is 2 to the x equals 4, so this is second order. That's that Fe compound. And I'm just going to shorthand it because it doesn't really matter, because, I mean, we don't care about this one, we only care about this one. So remember, rate equals the K times those two. So we're going to take the rate, and we're going to divide it by the Fe compound squared and the concentration of the iodine to the first. That's all set to be equal to K. I can choose any of these. I'm just going to choose the first one, 1 times 10 to the negative 5th. We're going to divide that by the Fe1 squared, 0.1 squared, and divided by the iodine to the first power, divided by 0.01. And for that one, did I do something wrong here? Look, I did not put 0.1 squared. I did not put 0.01 squared. I put 0.1 squared. So we need to go through here, and we need to insert a 0 there. Boom, and we get 10. That is C. The rate law for a particular reaction is rate blah if the initial concentration of B is increased from 0.1 to 0.3, that is tripling the rate. The initial rate will increase by which of the following. So we have K times A times B squared. And we just tripled the B, which is squared. So the normal thing here would just be KAB squared. Since we tripled this, that's going to be 3 squared, which is 9. So this would be 9KAB squared instead of just KAB squared. So it's 9 times faster for that. Consider the reaction of hydrogen with bromine gas yielding hydrogen bromide. At equilibrium, the concentrations of H2Br2 and HBr were found to be this, respectively. Calculate the equilibrium constant for this reaction. So we're going to need some paper. K sub BQ equals products over reactants. So the products will go up top. We're going to square that because the coefficient is 2. Reactants are going to go on the bottom. At equilibrium, they were found to be HBr is 1.71 molar. We're going to square that. And the other ones, H2 is 0.0082 and 0.0011. There we go. Calculator, 1.71 squared divided by 0.0082 divided by 0.0011. Get 324,179, which would just be 2 significant digits based off of these guys. That'll be 320,000, or 3.2 times 10 to the 1, 2, 3, 4, 5. Well, this is very big, so the products are greatly favored over the reactants at equilibrium. At equilibrium is, yep, so there we go, mostly products. Mostly products. Consider the following reversible reaction. At the particular moment the system is following concentrations, calculate the Q of the event. So K and Q are found exactly the same way. It's just that Q can be at any time and K has to be at equilibrium. So we have 2 squared divided by 2.5 divided by 0.3. We get 5.33. If K is 2.1, then there's a reaction favoring at the equilibrium constant. At equilibrium, well, let's imagine this. Imagine that this is the K of the one above it. Then to get to equilibrium, it would go in the reverse fashion, building more reactants and products, or favoring the reverse reaction. But this question isn't asking that, which is weird. It just says if K equals 2.1, then is the reaction at equilibrium favoring the product or favoring the reactant? Anytime it's greater than 1, it's favoring the product. Remember, it's products over reactants. Baron-Ryan shifts right, favors products, forward favored, and this arrow all mean the same thing. In a K expression, how are liquids or solids handled? They don't have concentrations, so they are given the value of 1. Of 1, which means if we square them or do anything to them, it's not going to affect anything. Le Chatelier's principle. So Le Chatelier's principle states that if we affect a system that's at equilibrium, it's going to maneuver to get back to equilibrium. So if we all of a sudden change something, the system's going to get back so that product over reactant is going to be basically fixed. Now, temperature can change that K. It's the only thing that can change that K. If you change the temperature, you're dealing with a different equilibrium constant then. But what type of reaction is favored by an increase of temperature? So in an endothermic reaction, we have heat as a reactant. And as an exothermic, we have heat as a product. So if we increase temperature, that's like adding more reactant. So that's going to force that to favor making products. So an endothermic reaction would increase, and temperature would basically make more product. How does a gas equilibrium respond if you increase the volume? If you increase the volume, then it will respond by favoring the side or the reaction that produces the most moles. So you have to look at the balanced equation. For example, here we have 2 and 2. So changing the volume is not going to do anything to that one. Down here we have 4 and 2. So if we changed the volume and made it bigger, it would favor making more nitrogen and hydrogen. What effect does a catalyst have? No effect. What effect does a catalyst have on a reversible reaction? It will reach equilibrium faster. Because both reactions will be sped up. How will the system respond if you add more reactant? A forward reaction favored. Forward favored. Remove some reactant, it will make more reactant, so the reverse reaction will be favored. Add more product, reverse reaction favored. What effect is adding or removing solid or liquid? If you remove all of it, then it will have to make a small amount. But other than that, there's no real effect there, unless you remove it all. How will each system respond to the following disturbances? Add H2, forward will be favored. Because we have too much H2, the system's going to use that H2 to make NH3. The N2 concentration will go down because it takes N2 to make NH3. Increased temperature. Since this is negative, that means heat is on this side. So if we increase temperature, it will favor the reverse reaction. Add a catalyst will be nothing, it's not applicable. Decreasing the volume will put a squeeze on the system, so it will favor the side with the least moles and make the 2 moles. Removing N2, system says, oh no, we need more N2 to be made, so that's going to be reversed because the reverse reaction makes the N2. Practice questions on this. Which of the following statements is true? When 2 opposing processes are proceeding at identical rates, the system is at equilibrium. opposing processes are pursuing identical rates. The system, that sounds pretty true. Catalysts are effective means of changing? No. The concentration, the only thing that can really change, no, that's not asking that. The concentration of the product equals the reactants. That's what people think, but it's not true. That's why we have a ratio, and if it's greater than 1, then there will be more products at equilibrium than reactants. If it's less than 1, there will be more reactants. So yeah, that's not true. Endothermic shift towards reactants when heat is added, that's false. If it's endothermic, we add heat, it's going to make more products. So the only one here that is true is A. Write the equilibrium expression for the following reaction. So K sub EQ equals products over reactants. And we need to take, that's a W, we need to take them to the value of, or take them to the power of their coefficient. So the coefficient is the exponent. If any of these were solid or liquid, we would simply put them in as 1 or leave them out completely. Calculate the equilibrium constant for the following reaction if the concentrations are this. So here's our reaction, products over reactants. So 0.1 square divided by 0.2 divided by 0.1. We're going to get 0.5, which is going to be C, 0.5. K, we don't have units for K, sub EQ. Consider this. Which of the following statements about equilibrium is false? If the system is heated, the right side is favored. Endothermic reaction, because it's positive. So if we add heat, it's going to favor the right side. So that's true. This is actually true. This is a heterogeneous equilibrium. They have solid and gas, so this is true. If the pressure on the system is increased by changing the volume, the left side is favored. If the pressure is increased, the left side is going to be favored because it has only 1 mole. This is tricky because people will count that, but that's a solid. So that is, that's also true. Adding more H2 increases the equilibrium constant. That is false. That is false. The only thing that increases equilibrium or changes K can be changed by temperature. For this reaction, we have this are placed in a little container. At equilibrium, the concentration is this. What is the value of K? Okay. So we got to find the value of K. So we have a little rice table here. A plus 2B yields C. And we initially have 3, and it's a 2, and it's 6. So 2 divided by 6 is 0.333. And 3 moles of B are placed, and that's going to be 0.5, right? And we have 0 of C. So what's going to happen here is we're going to lose some A, we're going to lose XA, and we're going to lose 2x of B, and we're going to add x of C based on the coefficients. So then this will be 0.333 minus x equals 0.300. So that's going to make x be 0.033. So then that will be at equilibrium for that. For here, this will be 0.033. And then we need to take 0.33 times 2, and we're going to take 0.5 minus that. Oops. It should be 0.033 times 2, and we're going to take 0.5 and minus that. 0.5 minus the answer of that. We get 0.434. So we have to take, okay, so C is 0.033. We need to divide that by A, which is 0.3. And then the B, we have to square it. So we divide that by 0.434 squared. And we get 0.84. I'm sorry, 0.584. Closest one to that will be here. Did I make 0.33, 0.3, up, 0.434 squared? Yeah. Minus 0.066, 0.4433. That's the closest we got. So we'll go with that, 0.589. Taking a look at number 6. A 3-liter flask initially contains this and that. A decomposition occurs according to this reaction at equilibrium. This is that. Determine the equilibrium of A. So for this, we're going to go ahead and set up another rice table. 3A yields 2B plus C. Initially, we got to do this again. 1.5 divided by 3, that's going to be 0.5, right? That's going to be 0.5 initial. And then we have some of B, but none of C. So 0.45 divided by 3. We're going to get 0.1, I'm sorry, that's some of B, 0.15 here. We have 0 of C. So we're going to use 3x of A to make 2x of B and 1x of C. It's just the way it has to happen because we don't have any C and the system is going to make some C. That's how it works. So then what we're going to do is at equilibrium C is 0.1. So that makes this our 0.1. That means we're going to get 2 times 0.1 plus 0.15. That's going to be 0.35. And that means we're going to get 0.5 minus 3 times 0.1, which is 0.3. This is going to be 0.2. So determine the equilibrium of A. Well, there it is. It's that 0.2. All right. Next time we will do... Oh, let's finish these off. There's some more of these. Solubility equilibrium and a KSP problem. So if we take a look, what is the molar solubility of silver carbonate? So silver carbonate breaks down, and this is solid, that breaks down into 2 silver ions and 1 carbonate ion. That has 2 negative charge. So we can ignore this because that's not going to be a factor. The KSP is equal to 8.1 times 10 to the negative 12th. So again, that KSP is just like the other Ks we were working with at equilibrium. We need the products over the reactants, but the reactant is going to be 1. So we need to get AG, and we are going to square that, and we are going to get CO3, and there's only one of these. So CO3 negative 2. We're not going to bother with that. And here's the deal. This is going to be plus 2x, and this is going to be plus x. They were 0 to start with. So that means that we're going to put 2x into the square times x for this one. So what is 2x squared times x? Well, that's 2 squared times x squared, which is 4x squared times x is going to be 4x cubed. So this is going to be our final formula for that. We're going to take 8.1 times 10 to the negative 12th. We're going to divide it by 4 to isolate the 4 there. And then we need to take the cube root of this. Well, cube root can be found right here. Answer that. And we're going to put that in 1.26, 1.27 actually. 1.27 times 10 to the negative 4. That is going to be the amount of this that dissolves. That means that this would be whatever 1.27 times 2 is, what, like 2.54 times 10 to the negative 4th, and this would be 1.27. So this actually has a unit that is molarity, because that's the molar solubility of that. Find the solubility of lead chloride if the KSP is this. It's found the exact same way. Again, we have PbCl2, Pb plus 2Cl negative. That's going to be a 4x cubed again, and we're going to set that equal to 1.6 times 10 to the negative fifth. So if you can see that, the other thing it could be is just equal to x squared. If both of these were 1, then it would just be x squared, but it is the same exact thing as the previous one here. So we're going to take that and divide it by 4. Then we're going to math that, and we're going to cube root it. 0.15, if we go to scientific mode, you'll see, oops, 0.01587, which was the answer before, becomes 1.587 times 10 to the negative second, which is our answer if we round it to 2 significant digits. That's going to conclude it for us. Thank you, and the next topic we'll go over is acid-base and oxidation reduction.